just set up the general idea of chemical equilibrium. Right? We'll start with the basics that you learned in Gen Chem, right? And just kind of standardize it. Right? Let's standardize the ideas of chemical equilibrium. You guys maybe remember ice charts in Gen Chem. Let's go back to that idea and see if we can learn a few things from that general idea of chemical equilibrium that we learned a very long time ago. Right. So let's just set up a generic reaction, reaction between two products that maybe generates some set of a set of reactants that generate some set of products. Okay. So let's say we start with some molecule A, and let's just keep things simple and keep it in as a gas. Right. So imagine we start with some A gas. And again, let's just make a note that we're going to assume ideal gas law here. Right. We're not going to worry about real gases at the moment. That defeats, like, we lose some of the bigger picture by thinking about that. And then we're going to react it with some other molecule B. Right. And this is going to be an equilibrium of some products C and D. Right. That we'll just say are gases for now. I've made some gaps in my reaction formula here. Because we haven't included stoichiometric coefficient, right? There might be 2 moles of A for every mole of B in this reaction, right? So we should consider generically reactions that have other distributions of other stoichiometries, right? So I'm going to call the stoichiometric coefficient nu, just this kind of squiggly A, or V, nu, A. That would be the stoichiometric coefficient for A. This is the stoichiometric coefficient for B. Stoichiometric coefficient for C, and the stoichiometric coefficient for D. So just as a note, V sub I is the IF stoichiometric coefficient. Right. And we want to make sure, of course, that these lead to conservation of mass on both sides, right? That you have the same amount of atoms on both ends, right? So we're going to have a balanced chemical reaction, right? We're going to assume a balanced chemical reaction. Okay, and so what I want to think about is, how do I use Gibbs energy? How do I use thermodynamic parameters we've learned to track where the system lies in equilibrium? Is it at equilibrium? Is it out of equilibrium? Do we have too few products with too few reactants? Where do we lie in terms of the material? Right. So our goal is to determine whether a reaction is at chemical equilibrium. Right? And we have to define what it means to be at chemical equilibrium. Right? You have an idea of what chemical equilibrium means, right? You let a reaction go and you have some distribution of products and reactants. And once it hits that distribution, it stays at certain temperatures and certain pressures. You have some distribution of reactants and products. And the equilibrium constant tells you that distribution, right? So let's assume, right? Let's ask the question. Imagine we started this reaction with just A and B, right? No C and D. Obviously, that reaction is not at equilibrium, assuming it reacts. And eventually, maybe we come back to the reaction and we have more C and D than we do A and B. Some of A and B is reacted. Do we have some confirmation that when we look at it the second time, that the distribution of products and reactants that we see is actually the equilibrium distribution? Or do we have to wait a little bit longer? Right? So you can think about the idea of monitoring your reaction and asking the question, are you in equilibrium? Are you done? And what I want to do is I want to use some of our thermodynamic properties to, one, determine where that point is, right? What is the distribution of A, B, C, and D that is the equilibrium distribution? And two, is there a way for me to measure or to quantify how far away the system is from reaching it? Right? Delta G will solve both of those problems for us. Right? We're going to use Gibbs free energy, which is again a function of N, P, and T. And this enables us to have a derivative of Gibbs, which is, as we've talked about, minus SDT plus VDP plus the sum over all the materials, right? I equals 1 to N, the different molecules of their chemical potentials times the change in the number of moles of that material. Right? So each material, each A, B, and C, A, B, C, and D all have values for the chemical potential. Right? There's going to be a different value for each one that tells you how the energy changes as you add or remove one of those molecules. Right? So the idea is that if I have some mixture of A, B, C, and D, that's an equilibrium. Right? I've let it sit there. Right? And do the Lashadi-Nice principle experiment. Right? I add some product, some additional product, or maybe some additional reactant into my mixture after equilibrium. Right? I've changed the number of moles that way. And let's say I've added some extra A after equilibrium. So D in N sub A is positive. I've added some moles. And what that means is that when I add those moles, the Gibbs energy of the system is going to change proportional to the chemical potential of A.
So I'm assuming that mu has something to do with mu, right?
With mu has something to do with nu. In a sense, yes, in the sense that these are going to be molar quantities and you're going to have different molar distributions. Yes.
Okay.
Because imagine if
Are
it's
they like
2 to 1. What's that?
Are they like proportional in some way?
Yes, they are. We'll come back to that. Yeah, absolutely. Yeah, hold on to that idea. But just think of it this idea like if we change the volume of our system, or sorry, if we change the pressure of our system, what happens? Well, the system responds by the volume of the system. And so, right, so the larger the molar volume, the less dense it is, the larger the molar density. If we change the pressure by 1 bar, the energy changes proportional to the molar volume of that material. Right? It's the same idea here. If we add 1 mole of material, the energy is going to change proportional to this value of the chemical potential. Right? So you can kind of think of it as like an energetic cost or an energetic benefit. It depends on the molecule, to adding or removing a molecule from the system. So now what I want to do, let's say I've mixed A and B together, it's reacted and it's formed some C and D. Right? I'll set the reaction up in the lab and then I run it overnight and come back. And what I notice, of course, is that the system is equilibrated in terms of temperature and pressure. Right, so imagine I take this reaction and I run it for a little bit. And I allow system to equilibrate. To some T and P. Right. I put it in a flask at some atmosphere and I just let it go. Right. So that means at this point, dG, the change in Gibbs energy at this equilibrium point is 0. And so at this point, the sum of all of these terms is equal to 0. Let the system equilibrate. But now what I'm going to do is I'm going to fix T and P. Fix T and P. I put it in a bath. All right, fixed here. Right, and so the DT term and the DP term, they turn off because the temperature and pressure are no longer moving. But the system fluctuates. The idea is that we're fixing the temperature and pressure so that they don't change. It's always 298 in 1 bar, for instance. So that these go to 0. So what we're left with is that if we have a system like this, ABC, that's a bunch of molecules that are in equilibrium with each other, and we fix the, if we fix the temperature and the pressure of the system, constant temperature bath, what we can say is that there's any fluctuations in the molecules, that the fluctuations sum to 0. All right, so if we make some products, right, imagine we add some products, then that means by definition that some reactants have to leave. Right? Because the total changes have to be 0 at equilibrium. The whole sum has to be equal to 0. Okay, so we have this condition. Which says that the sum over all the molecules in the system of their chemical potentials times the change in the number of their moles is equal to 0. Now, let me just think of a very simple idea here. Let's just simplify the problem just a bit. Right? Consider a very, very simple reaction, equilibrium between just A and B. Okay, so let's not worry about all the different ones. It's just 1-to-1 moles, right? So we don't have to worry about molar conversions. What this says is that the chemical potential of A times the change in the moles of A is equal to the change in the moles of B times their chemical potential times -1. So what this means is that every change in moles of products is equally compensated by a loss in reactants. Right? If one goes up, the other one must go down because the sum of them has to be equal to 0. Right? This is chemical equilibrium. Right? This is Le Chatelier's principle in the simplest terms, right? That when you change the conditions of the system will proceed along a route to bring it back to equilibrium. And so here, the Le Chatelier's principle we're thinking about is enriching the material, the system with A or B, depending on how you want to do it. And what it says is that as you add A, that means the only thing the system can do to react to it, to respond to that change, is to lose moles of B, and vice versa. And realize that they're equal and opposite to each other. Right? So I can add B, I can add products, and I get the opposite result of the reactants, and vice versa. Right? So this is reversible. It's completely reversible at equilibrium. And so what this says is that, right, at equilibrium, it is equally likely for a system to proceed forward, which means A to B, as it would be, or as equally likely as it is for the system to move backwards. Right? Because the changes in the energy are balanced with each other at equilibrium. Equilibrium, any change in A is compensated by a loss in B, and vice versa. Any gain of B is compensated by a loss of A. Right? So the two systems, this is what the definition of chemical equilibrium is that you have two things where any change in one is compensated by a change in the other in the opposite direction. Except there's chemical equilibrium. Kind of very simple way. Right? And there's a much deeper argument here. A little very subtle, right? That it's equally likely, right? In some sense, like think about Newton's third law, right? Every reaction is an equal and opposite reaction. In some sense, what that means is that any forward process also has an equally likely reverse process. In some sense, all physics that move forward can move backwards. It's time reversals nature. And this is exactly the same for chemistry. Any process that's forward moving is equally likely for the process to be backwards at equilibrium. And we have a special term for this in chemistry. And this is what's called the principle of microscopic reversibility. The connection between equilibrium and microscopic behavior is inbuilt into the definition of equilibrium. The fact of the matter is that the system has no problem, chemical reaction has no problem going forward and backwards. Now you have to think about that for a second, because I'm sure you can think of reactions that never go backward once they go forward. Right? For instance, combustion. Right? Combustion is a really good example. Right? You take a gas, a liquid, or sorry, an oil, some sort of oil, some hydrocarbon, and you take CO2, sorry, not CO2, O2, and you spark it and you make CO2 and H2O. Right? That's a really easy process to do. Right? So straight to you get tons of H2O, CO2. Right? Now, what about going backwards? Right? That's a real problem. Right? Right? Taking CO2 and H2O and combining it to make fossil fuels, if someone could do that, then we wouldn't really be worried about fossil fuels. Right? We could just recycle fossil fuels. Every time we scrub the CO2 out of the atmosphere, we can take it and convert it back to gasoline. So obviously we can't do that. Right? So you would think, okay, well, how do we have microscopic reversibility in that case? Right? That's a reaction that goes all the way to completion and it's unstoppable. Right? It's so unstoppable that it basically is an explosion. And again, this is a question of kinetics versus equilibrium versus thermodynamics. The fact of the matter is that if you take a hydrocarbon and some O2, and you put them together, imagine you just have one molecule, you just have the equivalent amount of stoichiometric molecules you need. So let's say you need 5 parts oxygen, 1 part fuel, right? And you've got a little container that has 1 gas molecule, 1 fuel molecule, and 5 oxygen molecules. Right? You have just the right amount of molecules to do 1 combustion. And what you find in those situations is that you go ahead and create the behavior and forward do the combustion reaction just for that small amount. What you find is, in fact, that the system can actually go backwards as well. That reaction is not as efficient as you would think it is. And so in some sense, the reason why combustion is so effective is the conditions in which we do it. But if you do a combustion type reaction at low density and low temperature with just a few molecules, you'll find that the system is not nearly as the reaction is not nearly as irreversible as you thought it was. That in fact the system does kind of linger and will go forward and go backwards, because every microscopic process in chemistry is reversible. It has a chance to go forward, which is a chance for it to go back as well. So we have to kind of rationalize that with what we observe in the bulk, which is that there are reactions that are in some sense unstoppable. And one of the reasons why combustion is unstoppable is because it generates 2 gases. And you're taking a liquid which is dense and containable, and you're combusting it in an open environment that releases multiple moles of gas, gaseous water and gaseous CO2. And that gas just escapes. Right? So how can you ever do microscopic reversibility if your products just leave? In that leaving process, right? What's happening is that when the combustion reaction occurs, here's your fuel, here's your CO2 and H2O. Right? What happens when we when we lose H2O or CO2 through loss of gas, right, this goes down. And once you work out the math, you find out that the only thing that's going to happen is the gas is going to continue to combust. Right? You use products, which means that more of the reactants are going to get used. Right? You have an uncontrollable process, not because the reaction is irreversible, but because of the process itself, the way that you're siphoning off the air, the gas is created, is driving the reaction forward. Right? So the way that we combust was constantly driving molecules using chemical potential from one to the other by removing the other one constantly. Right? So we have molecules coming in this way, these are going down, this drives more molecules in. Right? You have this runaway effect, which is why it's irreversible. But you can imagine that if you do it in a closed environment at sufficiently low energy and sufficiently low density, you end up just having an equilibrium between the two. Some of those combusted molecules will just fall right back into the fuel. So we have to balance those two things, right? There's this effect, this entropic effect, a steeping thing, this Le Chatelier's effect, right? Of where you lose molecules and it just keeps driving the reaction. Okay? So there's a consideration about entropy that we have to also make, which tells us whether a system is truly going to be irreversible or reversible in a bulk reaction. So let's explore that. I think it's important before we really start to think about equilibrium constants and entropy, is to really understand what these chemical potentials mean. Right? I think it's interesting to just think of them as individual contributions to the Gibbs energy that each molecule brings to the system. Right? Every time you bring in a molecule into the system, either A or B, it contributes some amount of energy to the system. And all this is saying is that any change on the left side in energy is compensated by an opposite change on the right side. That's all it's saying. Okay, so all this is saying is we have an energy balance. All right, so let's do a little bit of analysis of that. All right, so let's go back to our simple example. Between two gases A and B. Right, our equilibrium equation for this system is that the chemical potential of A times the change in the number of A is the chemical potential of B times the change in number of B is equal to 0. Right? That's our equilibrium condition. Right? Remember that these terms are proportional to Gibbs energy. So the units of these, right, the overall units of these are the same units as Gibbs energy. Right? So the whole set of these units should be kilojoules or joules. Right? We should have units of energy. Right? And of course, the units of DNA, should be kilojoules per mole. Right? The units of the change in moles is, of course, moles. Right? So what that means is that the units of mu A, right, needs to be kilojoules. Right? So what we could do is define our chemical potential as the change in the total Gibbs energy of the reaction with respect to the change in the number of moles of A, holding everything else constant, right? Which is T, P, and the number of moles of B. Right? And so what this is how much does the energy of the total system change as we add 1 mole of A or remove 1 mole of A? Right? It's just a change in total energy divided by the change in moles, right? So that has units of kilojoules per mole. And what you can show, and it's maybe not too hard to think about this, right, is that if you think about, earlier in the lecture, I just mentioned a comment about how the enthalpy of vaporization, right, the total energy of that reaction is just a difference of enthalpies of formation. So think about that from the perspective of Gibbs energy. Just replace enthalpy with G, H with G. There is a Gibbs energy of vaporization, right? And that Gibbs energy of vaporization is equal to the difference of the Gibbs energies of formation of the product minus the Gibbs energies of formation of the reactants. What is the Gibbs energy of formation? It's how much Gibbs energy, how much energy a mole of that molecule brings to the table. How much energy is stored, free energy is stored in that molecule. That's exactly what this is. The chemical potential is how much is the total energy of the system change as I change just one of the materials, right? And so this has to be proportional to the amount of free energy stored in a single molecule. So all these chemical potentials are just the delta formations of the G's for the materials, right? Which is just, you guys have been calculating these in problem set 2, just kind of indistinctly. Right, which is equal to the formation enthalpy minus T times the enthalpy or the entropy of formation of the material. Right, so these chemical potentials are, all they're measuring is how much energy does one molecule bring, or a mole of molecules bring to the table when you add them. Right, and so that should make sense at a chemical equilibrium where the change in Gibbs energy is 0. Then that means that whatever energy our reactants bring in as we add reactants has to be compensated by an equivalent loss of energy on the product side. The energy goes up on one end, energy has to go down the other one to maintain delta G is equal to 0. So these chemical potentials are just energies. They're just individual energies of each of the components. We know how to do the math of this, right? The only thing that's more complicated about this Gibbs math compared to what you're doing in homework 3 is that now you have enthalpy and entropy. Right? You just have 2 terms now, because we have to account for both of them. So let's think about that from the perspective of just a very simple diagram. So imagine that we have one of these little energy diagrams I've drawn over in the past. Right? Here's the products. Here's the reactants. And we're going to, on the y-axis, measure delta G. Or we'll just call it G. Gibbs energy. Okay, so let's say, we're just looking at A to B. Very, very simple reaction. We'll do something a little more complicated after this. Right? And then we go look up, right? You can just think of this as water vaporization, right? This is liquid to gas. The reaction is liquid, but partial gas. So we can go look up those Gibbs energies for the liquid and the gas, right? Because they're just H minus S. Right? That's the enthalpy of formation and the entropy of formation. The standard entropy.
So this is like energy versus the amounts of reactants versus products.
I'll show you that in a second.
Like
Let me draw it and you'll understand, okay?
Okay.
All right. So let's just say, for instance, that the reactants are less stable than the products, okay? So the reactants, let's just say, have some Gibbs free energy of formation right here, right? So this is delta Fg of the reactants. Right, times the number of moles of reactants that I have in my system, which we're just going to assume is 1. Right? And then let's say the products are a little more stable. So here's the products of delta F of G of product. Okay, and so the Gibbs energy of the reaction is just the difference. Delta reaction of G, right? And of course, delta reaction of G is products minus reactants. It's less than 0, right? Because the system is losing energy. So this is what we call a product favored reaction. Okay, so what does this mean? Well, this means that the system is at some amount of A or in some amount of B. So what happens to the energies if I start to add more material, right? So I let this reaction go, I form reactants and products, and then let's say I want to add some more A afterwards, see what happens. Well, what's going to happen? I'm going to add some products. I'm going to change or add some reactants, right? So the moles of the reactants are going to change. There's going to be some Dn. And how does the energy change with respect to Dn? Well, it changes with the change in gets total energy divided by the change in number of moles. It's just the chemical potential. So if I add some amount of moles, right, let's just say, for instance, here that the Gibbs energy of the reactants is positive, right? So we'll set this to be 0. Okay? Right, so let's say what happens is I add, so the system's at this energy difference, and I'm going to add some A. Okay? Well, the energy is going to rise proportional to the Gibbs energy of formation or the chemical potential of A. So my energy is going to increase. So say right here, right? Right, this is going to be mu of A DNA, right? I've added some energy, right? And of course, the energy increases as I add ends of A, because the chemical potential of A is its Gibbs energy of formation. This mu A is this number. And so that's positive number, right? So the energy increases for the reactants as I add reactants. But at equilibrium, what has to happen? Well, at equilibrium, any positive change on the left side is compensated by an equal and opposite change on the right side. So the system is going to react now by removing, right, this positive change is compensated by a negative change in delta G on the product side. Oh, wait, sorry. No, that's not true. Let's start over again. So I've made a mistake in my math. Let me explain what math I'm missing I made. Remember that the chemical potential is just the formation Gibbs energy. So the sign of chemical potential is the sign of the Gibbs energy of the material. So when I add molecules of A, this is a positive number because mu A, which is this Gibbs energy, is positive. DNA is positive. So that means this goes up. Right? And so what we know is that this product is equal and opposite to the product on the other side.
Okay, wait,
So
so
go ahead.
basically this chart is saying that if you're going this way, you're adding reactants and getting rid of products. And if you're going this way on the chart, then you're getting rid of reactants and adding products.
Yeah, you got it.
Okay, so, so if you're adding moles to the reactants, then wouldn't it be added farther?
Come back in a second. But let's just wait a second. So what do we know, right? So let's stop for just a second. So what we have in this example is mu A is greater than 0 and DNA is greater than 0, which means that the product of the two, which is the change in the Gibbs energy, is greater than 0. Okay? Now for the products B, the Gibbs energy formation is negative in this case, the way I've drawn it. It's a negative. Okay, so mu A is less than 0, right? But we know that by definition, mu B D N B has to be less than 0, right? Because if this goes up, this has to go down. Right? So if this is negative, then this has to be positive. Right? That's the only way to make the product negative. So DNB goes to 0. Right? So what
Is the second one supposed to say mu B? So mu A?
yes. Thank you. Right. This is equal, so I'll just write that. This is equal to mu B, and this is equal to mu A, which is less than 0. Right? So mu B is less than 0. It's got a negative Gibbs energy. Right? And we know that this product has to be negative because this one's positive. Remember, they're equal and opposite. And the only way to make this negative is that if the number of moles of your products increase. So what happens is that the energy of this decreases by UB, D, and B, right? And so now at these conditions, when I've added this A, this additional A, the Gibbs energy of my reaction is now different. It's greater, right? So delta reaction G prime, which is after I've enriched it with A, is, I'm sorry, it's less than, because it's negative, the delta reaction G at standard conditions. And so what that means is, so this is the conclusion that we have, because the gap is now increased, right? The energy of the products is lower, and the energy of the reactants has risen as we've added more A. And so now the difference is even greater. And so the reaction is now even more product favored than it was before. So the only conclusion here is that after enrichment of A, the number of molecules of B increases, and that the reaction Gibbs energy at these conditions, which I call prime, is even more product favored than it is at standard conditions. Okay, so this reaction generates more products as more reactants are added. Right? That's just Le Chatillier's principle. Right? The products and the reactants react to any perturbation or change in your system to reestablish equilibrium. And so if you have an increase in one molecule, depending on the value of delta G of the other one, you're either going to gain or lose molecules. Of course, in this case, you gain started product. So we're driving the reaction even more out of equilibrium, and it wants to create more products to compensate. Right? So this is just Le Chatillier's principle. For mass, right? For mass treatment. Of course, Le Chatillier's principle also applies to changes in temperature and pressure, which we'll look at later this next week.
But the equilibrium would still, like, it would still cross 0 at the same spot.
Right. So let's think a little bit. So what happens is this. So the initial difference in the energies between the reactants and products at equilibrium are these two lines. And so what happens is that Angie goes in and adds molecules of A. She sprinkles some more into her equilibrium mixture, which raises the energy of the reactants by this much.
And moves it by another.
Right, it moves it by that much. And so the system, in order to equilibrate, has to react equal in the opposite way on the other side, which is going to lead this to drop. And now what you have is an even greater difference between the products and the reactants, meaning that you're going to form even more products than you. As you keep feeding in reactants, it's going to form more products. So chemical equilibrium is about a balance of energies, right? We're basically replacing energy with mass, right? With moles, right? Each mole of reactants or products brings to the table some amount of energy. It has some heat, it has some entropy, has some Gibbs free energy associated with it. And the chemical equilibrium is determined by balancing the Gibbs energies of the reactants with the Gibbs energies of the products. And if you're off whack in equilibrium and mass, and you have more mole on one end to the other, the system will react in such a way to compensate for that, to reestablish equilibrium. Okay. So what I want to do now is I want to standardize all this. I want to be able to, instead of doing this analysis, which is somewhat instructive, but not particularly useful, in the sense that it's not very practical, right? Because in order to do this equilibrium analysis, we need to start thinking about chemical potentials and individual Gibbs energies, right? That's a complicated problem. So is there some way that we can take all this information and combine it into a single observable that tells us something about the state of the reaction at some point, whether we're equilibrium or not? Right? Is there some way that we can just get a number out of this, right? That tells us something about how the system is in equilibrium or whether it is or is. And also, so one, is it an equilibrium? And two, what are the equilibrium distributions of the reactants and the products? Of course, we really care about this stuff. So what I want to do is I want to do just a short derivation. I want to think a little bit about the Gibbs energy of a slightly more complicated reaction and see if we can come up with a nice formula that gives us a single number that we can measure experimentally that tells us something about the equilibrium conditions or the equilibrium balance of the reaction we're looking at. So let's go back again to this reaction scheme that I wrote a while back between A, B to form C and D. Okay, what I want to do is I want to track this reaction as a function of the moles of A, B, C, and D. Imagine that, I mean, that's a good way to think about this, right? If we want to think about equilibrium, maybe the first way we should calculate it by just counting, right? As we go through the reaction, count how many A, how many B, how many C, how many D we have. All right, so let's define some tracking numbers, ways to track the moles. All right, so let's assume initial concentrations or initial moles of Na, comma 0, right? So that's the number of moles of A at the 0th point, in B, comma 0, in C, comma 0, in D, comma 0. Okay, so those are our initial moles of each of the materials. I don't know what they are. They could be 0. They could be some giant number. It doesn't matter. Right? And then what I'm going to do is I'm going to define the current number of moles, right, which we'll call N sub A. Right? And that's going to be N sub A, comma 0. That's our initial conditions. And of course, if these are reactions, right, as the reaction continues, we should be losing them. So every time the reaction steps, we lose some number of moles. How many mole equivalents of A do we lose per step of the reaction? We lose mu A. Right? And we're going to multiply mu A by this number, that what I'm going to call the extent of reaction. I'm going to call it N with a squiggly. And this N is what's called the extent of reaction. You can just think of it as a number, right? It could be an integer or a number. It's basically how many times the reaction has proceeded, right? So you can maybe think of it as the number of, if the reaction is like a step process, every time, every so many milliseconds, there's a click. and the reaction occurs, and the extent measures the number of clicks. Right? So a number of clicks in a reaction, discrete reaction process. Right? Right. So after the first click, you lose, when you start with this many moles, and you lose this many moles after one click.
Is that linear to time?
Yes. Yes, absolutely. Yeah, it just tracks time. Yeah, you could absolutely just convert it into a time if you wanted. I don't know how often we're measuring, right?
Right, yeah.
But regardless, the value is going to be the same, regardless how often you click, because eventually you're going to hit it. There might be 1 million clicks, there might be 10 clicks. It just depends on the distance between the clicks. Okay, so we can finish up writing the rest of these. Right, and we lose B because it's a reactant. Right, and of course we gain C and D because they're products. So there's a plus sign instead. These should be equal signs. Okay. Okay. Now what we can do, let me just kind of write these here. Just going to come back to them. And let me move this so I have more space. There we go. Okay. So now what we're going to do is, so we have some function now, so we can track the number of moles as time as our reaction extent, as Angie says, right? So you can think of N tilde as a temporal quantity, maybe it measures the number of seconds. So we can track how much, so as a function of time, how much the reaction has occurred, right? And so now what we can,
So
go ahead.
just say that like N, the whole of N, you could say like the maximum quantity of N is like the amount of time that it takes, the total amount of time it takes for the reaction to be stopped.
Well, it could be anything. The question is we're going to ask is what value of N leads to our equilibrium. So these are going to be variables. These are variables. These are variables.
Yeah.
And we're about to set a constraint. And we're going to use this variable with the constraint to solve for the reaction.
Okay.
Yeah. Get back to me. Just hold on. So what we're going to do, right? So we have this reaction going, and we want to stop it at equilibrium. Right? That's kind of the reaction. So we want to see how things move until we reach equilibrium. And the reason why we want to do that at equilibrium is because we know exactly the condition for equilibrium. That's where the changing gives energy to zero. Right, so that we can apply the equilibrium condition which is that dg or delta G, however you want to think about it, is equal to 0. Right, and that just means that mu A d in A plus mu B d in B plus mu C d in C plus mu D d in D is equal to 0. And let me just be consistent. These should be uppercase, just to keep them consistent. So here's the trick, right? So you can see that we have these formulas for the number of moles at some given time, and we have this equation that constrains the changes in this number of moles. Like the sum of all the moles, no changes in moles, times the chemical potential is equal to 0. So we have this equation in terms of the chemical potentials and the change in the moles equal to 0. Then we have these formulas for the equate the moles. So all we need to do is take a derivative of this with respect to N and plug it into here. Get these of N. So let's do that. right? And in general, d sub n sub I, or let's say d sub n sub k, whatever k is, some letter, is going to be equal to plus or minus the chemical potential of that, or the stoichiometric coefficient of that material times the change in the extent. Okay, so I'm just taking the derivative of both sides. This is a constant, so it disappears. This is a coefficient, so it stays. And so any change in the number of moles is proportional to a change in the time, or the extent, right? Which makes sense. So D and K is proportional to the molar, the stoichiometric coefficient times the change in time, change in extent. Right? This is where the stoichiometric coefficients come in these factors. Because I can plug this in now. Right? Now I have mu A times the stoichiometric coefficient times the change chemical potential, or sorry, change in extent, plus mu B VB dn factorial plus mu C. Oh, sorry, I forgot some negative signs here. A and B should have negatives, right? Because there's a negative in the equations. There's two negatives here. So we have a negative sign here and a negative sign here. There we go. And then positive signs for the products. Sorry, I forgot this. This is dn tilde. Tilde is equal to 0. All right. So I've got a bunch of things there. I can kind of combine like terms, right? There's some things that everything is shared. Right? Everything is dn. So what I have is that dg all right, this is equal to dg, right? The changing Gibbs energy. So what I can do is divide both sides by dn, right? So that I have the change in Gibbs energy with respect to the change in time is equal to Vc mu c plus nu d mu d minus Va mu A plus mu D mu B mu B. Right, so there's mu and nu, sorry. Nus and mus. So I've just gotten rid of the dn's and I've just rearranged the terms. Right? And so I have these terms, these chemical potentials of the products minus these chemical potentials times the reactants. And each one is multiplied by the stoichiometric coefficient. Now, what's our definition of the chemical potential? It's the Gibbs energy of formation of the material. So this is equal to the stoichiometric coefficient times the Gibbs energy of formation of C plus the Gibbs, or the stoichiometric coefficient times the Gibbs energy of formation of D minus the same thing for the reactants. And there's a lot of alphabet soup here. But this is just the sum of the Gibbs energies of the products minus the sum of the Gibbs energies of the reactants. What is that? That's just the Gibbs energy of reaction. Right? So this is equal to the sum of the Gibbs energy of formations of the products minus the sum of the Gibbs energy of the reactants right? Which is just the Gibbs energy of reaction. It's a lot of math. Yeah. We're almost there. I have a relationship between a derivative and Gibbs energies and stoichiometric coefficients. So here's an interesting thing. So let me go ahead and write this down. All right, so I'm going to copy this over and go to the next page. I know this is a long, drawn out derivation, but we're going to come to a value that you guys all know and appreciate. Now, what I'm going to assume here, like I did before, is that A, B, C, and D are gases. Right? And so what I can say is that each gas has a partial pressure they each contribute some P sub I pressure such that the total pressure of the system, P total, so the P, is equal to the sum over all the little partial pressures, right? For this system, that would be PA plus PB plus PC plus PD. Okay. And we haven't derived this equation yet, but what we can show that as a function of pressure, the delta G, the difference between the delta G at standard conditions and the pressure at some other pressure, let's say P sub I. And of course, this is assumed 1 bar. Right, so maybe your gas is less than 1 bar. This difference is equal to RT logarithm of the partial pressure divided by the standard pressure, which is typically determined to be 1 bar. Okay, so the Gibbs energy as a function of pressure varies for gases. Working for gases. This is a different equation than what you had in problem set 3 on equation 1, but those are solid, they're not compressible. This is a compressible material, gas, and you get this logarithm in terms of pressure. Not a hard equation to derive. It says that the Gibbs energy varies with the logarithm of the pressure times the change in temperature, right? By the times the temperature. All right, so I can relate the concentrations or the pressures of my material to the Gibbs energies of the material. Right? If I know the standard Gibbs energy, standard conditions, I can calculate the Gibbs energy at any partial pressure by using this one. All right, so what I can do is I can plug this into my equation up there. I'm going to get rid of these stars here. I apologize. They should not be here. I can plug this in above, plug this into my equation again, above. I'm not going to work through the algebra just to save time. But it's just a simple plug and chug. And what we find is that the change in Gibbs energy of this system is equal to the standard Gibbs energies of the products minus the standard Gibbs energies of the reactants, just like we had before. Right, so this whole thing right here is just delta reaction of G. Right, so this is the Gibbs energy change at standard conditions plus RT times, I'm sorry, let me get rid of that log, times a rather nasty equation, but it's going to simplify a lot. Vc log of the partial pressure of C times the standard pressure plus Vd log of the partial pressure of D divided by the standard pressure minus UA log of PA over P naught minus UB log of PB over P naught. All right, so we have this. So what we see is that the change in Gibbs energy in this equilibrium process, as we start with some amount of A, some amount of B, C, and D, it changes, and the total change in energy is equal to the standard Gibbs energy plus RT times this equation that has something to do with the pressures, or in some sense, the concentrations of each of the gases. Right, the partial pressure. You can see the partial pressure is proportional to the concentration at constant volume. Right? You have a 1 liter material. The partial pressure just tells you how many moles per liter you have, which is just the molarity, right? So this is partial pressures are in some sense the same as concentrations, or gas phase concentration. So we've got this equation in terms of the logs of the concentrations of the gases times their stoichiometric coefficients. But what do we know about when you have a number times the log, you can bring that number and exponentiate the R. Remember that the x times the log of A is equal to the log of A to the x. So I can take this term, right, and use two rules. Yes, you got it. You got it.
That just to get to K.
X ln A is equal to ln of A of X, and ln of A minus ln of B is equal to the ln of A over B, and the ln of A plus the ln of B is equal to the ln of A times B, right? You've used these before. If you use all of these, this final equation becomes RT times the log of the partial pressure of C raised to the mu C power times the partial pressure of D raised to the mu D power divided by the partial pressure of A divided by the standard pressure divided by the stoichiometric coefficient of A times PB times the standard pressure times the stoichiometric coefficient UB. So what we have are concentrations of the products raised to their stoichiometric powers divided by the concentrations of reactants raised to their stoichiometric powers. As Connor noted, the system equilibrium. So what we can now have is that the change in Gibbs energy of a system at equilibrium, some conditions, is equal to the standard Gibbs energy change plus what we call RT ln Q, where Q is the reaction coefficient. Right? This is what we call Q right here. Right? It's just the equilibrium coefficient. Right? But notice that this is defined at any set of concentrations. Right? I can have zeros in the numerators, and things can be zero here, and I can still define a number. Right? So let's imagine that I'm not at equilibrium. Right? I don't have an equilibrium set of material I don't have an equilibrium set of of quantities. And so what that would mean is that the delta G that I would measure is off a little bit from the standard delta G. Right, so what that would mean then, right, because we know for an equilibrium, right, for an equilibrium, delta G needs to be 0. So if this is non-zero, that means we're not at equilibrium. So let's consider that. Right, so we now have this equation that says, right, this is our equilibrium equation. Which says that delta G, which is the Gibbs energy at any condition, at any point, is equal to delta G naught. That's the standard Gibbs energy. Plus RT when Q. We call Q the reaction coefficient, which we'll talk a little bit. You can convert it into concentrations, right? It kind of looks like, not exactly. We'll have D to the new D power times C to the new C power over A times the new A power times B to the new B power, right? It's not quite concentrations. Partial pressures are not exactly molar concentrations. There's a conversion between the two, but it's proportional, right? So these can either be partial pressures, concentrations, densities, EPC. There's lots of different ways to represent this system. All right, so how do we know the system's at equilibrium? Oh, at equilibrium, right, when the system is finally stopped, that means that delta G for the system at that point is 0. Right? That's the definition of equilibrium. Thermal equilibrium. With delta G 0, everything is settled in, and right, this is starting to equilibrate into soup. My delta G is starting to approach soup. And so when delta G is equal to 0, right, that says that delta G circle, right, the standard Gibbs energy is equal to minus RT ln Q. Right? So at equilibrium, Q tells us, well, you can look at it either way. Delta G of the reaction at standard conditions tells you what the value of Q will be, right? The concentrations, or if you have the concentrations, you can measure delta G. Right? So we rename this. Renamed. Q we call at equilibrium K sub C, or sorry, KEQ, which is the equilibrium constant. All right, so we finally have an expression now that says at equilibrium, delta G naught is equal to minus RT ln KEQ, or KEQ is equal to e to the minus delta G over RT. Right? Yeah, so you guys can have trauma that you spent 30 minutes deriving something that you've seen for like 10 years.
Yeah.
But now you understand where it comes from.
I have it on my arm.
So there you go. So the equilibrium constant is just a way for us to convert between a balance of individual microscopic energies of each of our materials, setting the equilibrium condition, which is that the total change across all the materials is equal to 0. And that is satisfied that when the equilibrium constant or rather that the delta G is equal to the log of the equilibrium constant times RT. Look at this form of this equation for KEQ. Remember, equilibrium constant is like a fraction, right? It's the fraction of products over the amount of reactants you have, right? Kind of. Right, some fraction. And what it says is that the fraction of, say, for the fraction of products relative to reactants is equal to E to some minus energy over RT. This looks like the Boltzmann equation, and it is. This is just a restatement of the Boltzmann equation for a system at equilibrium, or sorry, at constant temperature and constant pressure. Right? This is just Boltzmann's equation. Right, which is that Ni over N total is equal to E to the minus EI over RT, right? That's what you did in problem set 1 or problem set 2 for systems at constant pressure. And chemical equilibrium. Right? So what happens is that when you put a system at some temperature, give it some heat, and put it at constant pressure and allow it to equilibrate chemically, you get an expression for the fraction of excited or products over reactants, and it's equal to Boltzmann's equation for that energy. Right? We just come back to thermal equilibrium. Right? So equilibrium, chemical equilibrium is nothing different than heat. It's just now that the heat that is being created is by discrepancies in number of moles of molecules, right? Some molecules will increase the energy, some will lower the energy, and it's about balancing the two. Right? And when everything is balanced, we're at equilibrium, and then the rules that we learned about thermal equilibrium apply again. We just give them different names. We'll take all of this. We're done with derivations for a while. We'll come back to this and do some applications, look at some different examples, and see how we can break this. Okay? All right. Have a good one, guys. Have a nice weekend. Happy Halloween. I don't have a costume this year, sorry. Oh, thank you.
I was gonna say, can I use this marker just to draw out real quick?
It's dead.
Oh,
I'm
it's
pretty
dead?
sure. You want to just draw one here?
I can.
Yeah, here.
Just because, well, I was gonna go to a presentation in 10 minutes, so I'm gonna try and be quick with this. So,
Oh, you're going to the forensic science one?
yeah.
Okay.
Yeah.
Can't wait for my computational chemistry exam tonight.
Oh, good luck.
Thank you.
I'm just writing this out so I can see it.
Yeah, no problem. Take your time.
Oh, no, I gotta be quick because I don't want to be late. I was late to something else the other day.
That's okay. Angie, were you tutoring someone yesterday?
Huh?
When you were sitting with us?
Yeah,
Are you an LA or something?
no,
You're just helping?
yeah,
Oh, that's nice of you.
yeah. Have a good one.
Yeah, you too. Thank you. What's up, Isaiah? Yeah. Can you do me a favor, ma'am? Jimmy? Yep. Appreciate it. All right, what's up? Let's start. Uh-huh.
So I realized the way that I did before, it's wrong. I got rid of five. But then I think this is a whole mess. I started doing it out. And I got to
I think that's right.
but I got there with the operation.
Okay.
And I heard from other people, they're doing it from 298 to immigrant from 298 to 678. I did the reverse. That's what really changed.
You change the sign.
Which changed the operation. So I just kept it there. And then after messing around with it before, I got what people were getting. Yeah, not for the 35 decades. That gets me to let me see what you are on that end.
I'm gonna stop writing here because I can kind of explain my question from here.
Yeah.
So my problem is once for one integral, right? It's just, you do one for the gas, one for the liquid, right? This is how it would be for all of it, right? Temp final, temp initial.
Yeah.
And that's divided down. So
Because it should be because what this is gonna come out to is AT plus BT squared over two
Mhm.
plus blah, 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 evaluated from TF and TI.
Mhm.
That's gonna be
You write so much quicker than me.
ATF, well, I've been writing on this for years, so ATF plus BTF squared over two minus ATI.
Okay, I see.
You see where the foiling is wrong? So the B term is going to be B times TF squared minus TI squared, not the. difference
Okay,
squared,
yeah,
right? So,
yeah, I just. put square.
let me show you a little hint, with the NIST stuff that actually saves you time. It's the exact same thing that you're doing right here. They've just done it for you already.
I'm gonna look at it as well. Yeah, let me.
No, just, yeah. In the, oh, sorry, this is the wrong molecule. This is deuterium oxide. Oh, they don't have as much data. So if you go down to the show me an equation.
Yeah.
It's just that it adds a couple of different numbers. Because it's, what they do is their initial So this is the constant term. That
I had it as the wrong answer.
So if we want to start at 373, do we? Where the two
No, so you can use this, and what you're gonna do is when you calculate this at 298, it's gonna come to 0. And so what you can then do is calculate this difference as 373. And what you'll see is that the enthalpy of 373 is,
And I mean, difference lower than I actually.
let's say like minus.
Yeah, I wonder if like.
So 373, this difference would be -3.
I got it on
So
one
if
point.
you know the enthalpy at
On that last question, you know,
373,
point I lost.
and you know the difference
And I
between
can put it next to my final.
298 and 3,
number down.
you can calculate the program.
So yeah, it's.
Does that make sense?
Is it by flipping the sign or?
Yeah, well, think of it like this, like,
It's always like.
sorry, let me just write it here, right? So just say for instance that you calculate, so you have that the enthalpy of vaporization at 373, let's just say it's 40 kilojoules. Right, and you go type in, you go do that formula and you find that H of 373 minus H of 298, which is what that equation gives you, is -3. And so that means that the 298 one is 3 kilojoules per mole higher than that. Because H of 373
Okay, yeah.
is -3 plus H of 298. So you can solve for this.
It's been a while since I've had to fully work out an integral, and so that's why it's like.
Right.
That you throw it on there and everything else was making sense.
Some people did them by hand,
Yeah.
and you're doing the exact right thing other than this.
Yeah.
And it will give you the exact same result that those just.
That's what that is.
Okay, so I am gonna switch to that.
Okay, yeah, it'll save you some time.
We have to get the.
All right, thank you.
Yep, you're welcome.
See you on Tuesday.
Okay, I'm sorry, guys.
That's okay. No, you're welcome. I'm just chilling.
So let me.
See you guys there.
See ya. And
I'll see you tomorrow, Jimmy.
so for the the entropy initial that we add to it, it's supposed to be the enthalpy at 373 that we calculated.
Yes.
Or no, the 40.7 over 373, right?
Yeah.
Because,
Because delta G is 0.
Yeah.
So H is equal to T.
okay, so then, because then that changes this answer as well, because this is using something else that other people were using. Okay. Because then that becomes, well, it should be 109 to 105. And then,
Yeah, that's a little low. So if I get this value, 103.5.
are you? I don't know. What do you get as like just the change? Like when you add up the values before,
Well, look, I have 109.5 from 373 entropy, so the change is -6.
so it would be this, this.
Yeah.
Okay, so this, okay, awesome.
I don't know why that's where I had to look at more carefully, but I did all this by hand, so I don't know how you're doing it exactly.
This one,
Oh, you're doing ABCs and DBs.
yeah, so I
Okay,
did the
yeah.
individual terms that you see here, there's the natural log
Yep.
difference. there's
Yep.
difference divided by 1,000.
Yep, you're doing exactly the same thing on cost, because this is the equation I have, which is exactly what we've done.
Yeah, I did that in Excel, and then I
Yes.
just added everything together. I did addition because I did it from
That's
273 to.
Yep.
Okay,
Yeah, you guys, awesome.
thank you.
Yeah, no problem.
Yeah, I don't know how I got 105 yesterday, but it was not correct. The way that I did it. But
That's pretty close.
Yeah, but I wasn't satisfied with the fact that I got it wrong, right? The wrong way.
Yeah.
Then after realizing that, I spent even more time trying to figure it out, and then I got that.
I'm glad you figured it out. Yep, no problem. See you tomorrow.